Hello everyone. Greetings for the day. I am Shashwat and I am an assistant professor at IIT Mandi. I'll now present an interesting research which I am conducting at IIT Mandi, funded by the Anusandhan National Research Foundation, Government of India. The talk is on investigation of the influence of magnetic fields on small-scale turbulence in thermally driven flows of liquid metals. Such flows are called magnetoconvection. So, to give it a formal definition, magnetoconvection is buoyancy-driven convection of electrically conducting fluids in the presence of magnetic fields. Buoyancy-driven convection means if a fluid has temperature gradients, hot packets of fluids will rise up due to buoyancy and cold packets will come down, resulting in convective heat transfer. Furthermore, if the fluid is electrically conducting, imposing an external magnetic field will alter its dynamics. A current is induced due to Faraday's law, which interacts with the magnetic field to generate an additional body force, the Lorentz force. Magnetoconvection occurs in some engineering applications and appliances, such as continuous casting processes, liquid metal batteries, and cooling blankets in futuristic fusion reactors. It is ubiquitous in solar convection, chiefly responsible for sunspots and solar flares. We'll focus on liquid metal convection aspects in this project. Now, magnetoconvective flows in the above applications is highly turbulent. Hence, we require appropriate subgrid scale models for simulating such flows. Building such models require detailed knowledge of intermediate and small-scale dynamics of turbulent flows, as well as interactions between the different scales of motion. Now, the dynamics in these scales do not depend on the geometry of the domain. Hence, our aim of this research is to study the turbulent liquid metal magnetoconvection using direct numerical simulations on a simple cubical geometry. We simulate turbulent liquid metal magnetoconvection in a rectangular box, which is heated from below and cooled from above with a vertically imposed magnetic field. We use three different strengths of magnetic field quantified by the Hartmann number, HA, and adjust the buoyant forcing, which is quantified by the Rayleigh number, or RA, such that the intensity of turbulence remains the same in all the cases. The first plot, I am showing the plots of the Hartmann number and the non-dimensional heat flux, the Nusselt number versus the buoyant forcing. We can observe that the heat flux increases marginally as the magnetic field strength increases. This is probably due to the increase in the anisotropy in the flows, as observed in the lower figures, where we display the contours of temperature superimposed with velocity streamlines on a vertical midplane. The anisotropy breaks the symmetry between the upward and downward heat fluxes, resulting in enhanced net heat flux. We also simulate turbulent liquid metal convection at molecular Prandtl number of 10 to the power minus 3 in a rectangular box for several strengths of buoyant forcing, and we compute the scale resolved turbulent Prandtl number. The turbulent Prandtl number is an important quantity in turbulence modeling, and it is the ratio of eddy viscosity to the eddy diffusivity. These quantities refer to the enhancement of shear and heat flux due to turbulence. For the first time, we show that the turbulent Prandtl number has scale dependence, and it decreases with an increase in the length scale. It is also interesting to note that although the molecular Prandtl number of the fluid in this case is 10 to the power minus 3, the turbulent Prandtl number lies between 1 and 10 depending on the scale. Now, what are the main impacts of this work? As explained in the first slide, liquid metal magnetoconvection finds applications in the next generation and potentially highly sustainable energy systems such as cooling blankets in fusion reactors and liquid metal batteries. Also, our findings are expected to be relevant in solar convection and behavior of sunspots. These sunspots lead to solar flares that travel millions of kilometers, profoundly impacting satellites and damaging their electronics. That's all in this webinar. If you're further interested in our work, please refer to our recent publication in the Journal of Fluid Mechanics titled Scale Resolved Turbulent Prandtl Number for Rayleigh-Bénard Convection at PR is equal to 10 to the power minus 3. Thank you for staying tuned. Goodbye and have a nice day.